Hello and welcome to my Advent of Code series for 2020. If you've missed any of the previous episodes, be sure to check out the playlist with those right up here. So today we are going to jump into the day 7 problem, Handy Haversacks. So here the story behind it is we land at the regional airport in time for our next flight, and they're having an issue with their luggage processing because they have very strange luggage rules that require certain colored bags with certain other colored bags within them. This is probably the most convoluted setup we've had in a problem so far this year. We have a list of rules laid out exactly like this. This is not flavor text. This is how the actual input file looks. And it shows the specified contents for different bag types. So here, for example, every light red bag has to contain one bright white bag and two muted yellow bags. And we could follow those down and see that a bright white bag contains a shiny gold bag, and on like that. And you have a whole network of things like that. So for problem 1, we have a shiny gold bag, and if we want to carry it in at least one other bag, how many different bag colors would be a valid color for the outermost bag? So how many colors can eventually contain at least one shiny gold bag? So it gives us a quick example here and breaks it down for us. And we are going to need to do it for our list of rules, which is way longer and way more complicated. So this one is a bit of a harder problem in at least how I think. There may be easier ways to do it conceptually, but I'm going to show you what I think is the most elegant way. I highly recommend you give this problem a try before you jump in here. Pause this video now and go ahead and do that. And we're going to jump into my code right about now. So the way that I ended up deciding to do this is tackling this as if it was a weighted directed graph. So I've been learning graph theory recently, and it seemed like the data structure that made the most sense for this. So to do this, I coded up a quick interface here with a definition for a node, where a node has an ID and a dictionary of the things that are adjacent to it, and each of those things adjacent to it get a weight. So with that, and I've sort of defined it in a way of having parents and children, where parents are things with negative weights, and children are things with positive weights. So I created that. I added a way to add other nodes to its neighbors, or adjacent in this case, because I called them parents and children, so they're not really neighbors in that parlance. So that, and then I added a way to see all of our parents, which will just give us a filtered version of that dictionary, essentially, where we have all the ones with negative weights, and a way to get children, which is the same thing, except for positive weights. Then I also added a get edge thing where you pass two things together, and it will give you the weight of that connection. This didn't end up being necessary because I changed these to include the entire dictionary instead of just being a set of IDs. So then on top of that, encapsulating that, I should say, we have the graph class. So what the graph class has is essentially just a dictionary of nodes. And the things that we can do with it is we can add nodes, which will add an entry for the node ID with a node object containing that. We have a get node function that is going to take in a node ID and get us the actual node object so that we can do things to that. And then we have an add edge thing right here, which what that does is it takes in a parent, a child, and a weight. It checks if both of those nodes exist. If they don't, then it goes ahead and creates them. And then it adds adjacent things for each of those, for both the parent and the child, where the parent and child will have a positive weight connection, and the child and the parent will have an inverse negative weight connection. So the way that this data structure is encoded is not exactly how you would probably encode a directed weighted graph, because you would probably just have the direction and the weight instead of having essentially two vertices with differing weights. But this is just the easiest way to do it for this problem. So the next important thing, and this is probably this is at the core of this puzzle, is how you actually parse your input. So that is what we do in this read rules function right here. So what we are doing here is we are creating a graph. We are opening our input file. We're splitting it by line and looping through each line. So then if I am to go ahead and jump over to how our input files look, you'll see that it's just these strings of text like this. So the way that we can split that down is first we split it on bags contain, and then I was having issues with spaces, so I just sort of blindly added strips everywhere. Some of these may not be necessary, but whatever. So then what we're doing is we are adding a node for each thing for each key.strip. So key is the first element of the line.split on bags contain, which is going to give us, in this case, mirrored tan or striped red or anything like that. So we're adding that, and then if it has no other in the line, we can go ahead and find an example of that. Right. So no other, the only form that has no other is like muted purple contains no other bag. So that means it has no children. So at that point we can start parsing if that's the kind of line that we have. So then if it doesn't have that, then we are then going to split our contents line, which is the thing after the bags contain. So that's like 2 muted beige bags, 3 wavy beige bags, whatever like that, or 2 mirrored tan bags, things like that. We're going to split that down into a list on the commas with spaces, which you see is how each of these are split up. And then I loop through those. I split those down into tokens again, so that will then give us 5 shiny blue and bags. And then we add an edge for key.strip. Again, I'm just very paranoid because I had extra spaces somewhere before and I just wanted to make sure I caught them. And then we are joining the item tokens between the second element and the last element and stripping that as well. So the reason that we do that is because, so if we have 5 vibrant plum bags, the actual node that we want is just vibrant plum. So we are taking, instead of those, we just end up having 5 and bags. So that's what we want there. And then finally, we have the first element of our item tokens array is going to be our weight. So I convert that to an int and use that as our weight. So once we run through that, we can go ahead and return rules. Rules is going to be our graph exactly how we want it, with every single vertice and every single edge defined perfectly. So once we have that defined, we can jump into our actual solution. So for part 1, the way that I did this is we're essentially just trying to find the different bag colors that can eventually contain a shiny gold bag. So what I did is I created a set here called valid. Then we have our start node, which is going to be shiny gold because that's what we want to find what things contain. And then we have a set of things that we have to process. So that's going to start off with our parents of shiny gold. So since we don't want the weights, I just get this down to the keys. And pretty much what we're getting here is we are getting all of the different bags that can directly contain a shiny gold bag. So then what I do is I have this while loop right here, which is while the length of toProcess is not equal to 0. So while there are elements in this set, essentially, then we go ahead and pop. And when you call pop on a set, it just grabs a random element because it's unordered. And that's perfectly fine for us here. There's no need for any sort of ordering. So then we get that, and that will give us our current key that we're working on right now. So for example, it'll give us one of the things that's a direct parent of shiny gold. And then what we do is first we add to toProcess using update. So what happens with update is you go ahead and pass it an iterable, and it will add all of those things to your set, everything in the iterable. So we add rules.getNode cur.getParents.getKeys. So we're essentially adding the parents of whatever is happening in this loop back into our toProcess loop, back into our toProcess set, so that those will also eventually get looped through. And then we add to our valid set our current thing that we're processing. So what this will do, if you think about it conceptually, is we have a set. It has all of the parents of shiny gold in it to start, all of the direct parents. So it will, at some point, it will get through all of those parents of shiny gold, but while it's doing that, it will also be adding the parents of the things in shiny gold to our toProcess set. And eventually looping through all of those until we eventually end up touching every single kind of bag that can eventually contain a shiny gold bag. So with that, once we have that done, we can just send back the length of our valid set, and that will give us pretty much the number of kinds of bags that can contain a shiny gold bag at some point. So the reason why valid and toProcess are both sets is because there is a case where you could have, for instance, let's say a vibrant plum bag could contain a faded blue bag and a shiny gold bag, but then a vibrant blue bag, or no, what did I say? I completely forgot what I'm saying, but whatever. The blue bag could then also contain a shiny gold bag, and we don't want to end up adding that blue bag type to our list twice. Because we're that plum bag to our list twice, because what's going to end up happening is it's both a direct parent of shiny gold, but then it is also going to end up being a parent of shiny gold. So if we use these as sets instead, then we're not going to have that issue, and we're not going to have a situation where those things get counted twice. So once we do that, that is going to be our answer for part 1, and we can jump on over to part 2. So for part 2 of this challenge, it's getting pretty expensive to fly these days, not because of the ticket or anything, but because of the obscene number of bags that we need to buy, because everything has to fit this exact thing. So consider our shiny gold bag and the example from above. So all our shiny gold bag has to contain these bags that like these other bags, and then these other bags have to contain other bags still. So even with this super simplified example, having one shiny gold bag requires you to end up having 32 bags nested together. And then in the slightly more complicated example, it's already up to 126 other bags. So the question for part 2 is how many individual bags are required inside of our shiny gold bag. So we have one shiny gold bag. How many bags does that mean we have to have because they have to be inside of a shiny gold bag? So I recommend you go ahead and give this problem a try. If you may have been stuck on it before, maybe with my sort of idea of the graph theory approach to this, it will make it a little bit easier. And we're going to jump ahead into my code right about now. Okay, so for part 2, what we are doing here is essentially just a different graph traversal to what we were doing before that's slightly more complicated. So I ended up deciding on using a recursive approach to this, using a function that I wrote called getNumBags. So what getNumBags does is it essentially passes back how many bags an individual bag actually represents. So let's say you have a faded purple bag and that has to have 5 vibrant blue bags in it. So then that faded purple bag isn't actually one bag, it's actually 6 bags because it's the one vibrant purple bag and the 5 blue bags that are inside of it. So what this function does is it recursively is going to find how many bags are in a certain bag type. So what it does is it gets the actual node of that bag type, it finds all of its children, and then if the length of children is 0, that means that this bag doesn't have any other bags inside of it, and it's just a bag, right? So then it is essentially only representing one bag. But in the other case, it's both representing itself as a bag, which is the reason for this one, and it's also representing the sum of all of the different types of bags that are inside of it multiplied by the number of times that bag is inside of it. So let's say we have a purple bag with 5 blue bags, and every 5 blue bags has 3 white bags. So then and every white bag doesn't have anything else inside of it. So then every purple bag is not only itself, but it's also the 5 blue bags times the 3 white bags. Times the number of bags that each of those blue bags represent, which is actually 4 because of the 3 white bags inside of them. So if we go through this recursively and we build up like that, then we will eventually get our answer for how many bags a shiny gold bag represents. But that's not our exact answer because it didn't want to know how many bags do you need, including the shiny gold bag. It just wanted to know how many bags do you have to have inside of your shiny gold bag. So then for my actual part 2 function, I run this recursive function on shiny gold, and then I just subtract 1. So then our main is just our standard main, the way that I've been doing it all of these other times. So that is it. I'm sure there are a ton of other approaches to this sort of challenge. I would love to hear your thoughts and how you ended up solving it if you did use a different method to mine in the comments below. So be sure to tell me that. Be sure to subscribe so you don't miss any future episodes in this series or any of my other series. I'm currently doing one where I teach how to use a Unix shell. It looks like the problems are really ramping up now, so I'm very excited. I think we're going to see some incredibly interesting problems with really cool solutions in the future. So be sure to get subscribed so you don't miss those. Check out the playlist up here if you have missed any of the previous days of Advent of Code and you want to try them out. And I will see you in the next one. Goodbye.